So this project is Precision Mechanics Applications of Metal Fusion Fastening Methods, sponsored by ASML. And the purpose of this project is to create a concept that can replace or enhance the company's current large bolt fastening method used within their lithography machines. The team is to research different types of fastening methods and produce a prototype. So the project scope was divided into 4 possible product functional categories with a fixed bottom plate, meaning the top plate can be non-adjustable, in-plane adjustable, out-of-plane adjustable, or in and out-of-plane adjustable. And then each product functional category was further divided into permanent, replaceable, and reassemblable joints. And then specific functional requirements were listed for each. The team decided to narrow down the project scope to in-plane adjustable designs. And some notable requirements include it must be operable at high accelerations, must withstand microslip in plane, has to have a high amount of shear strength, has to have a high resolution of in-plane alignment, and then freezing does not affect initial in-plane alignment. And now for our design, it is in-plane adjustable and reassemblable with original parts. Cone piece cradles a sphere and is spot welded to the upper plate to fix the system once it is aligned. The sphere fits chamfers, allow for a high degree of repeatability. Spherical washer compensates for tolerance differences and uneven surfaces, and it is compatible with the spot welder shown in Figure 5. And the upper plate has clearance holes and can be adjusted to the amount of clearance left within the holes when it's bolted. And the lower plate is threaded with countersink holes, which fixes the system to allow for adjustment in the top plate. So the team decided for 2 methods of testing, including a Sharpie impact tester and an Intron tensile test. And an optical sensor was integrated into the prototype of the knife edge and will be used to test the system's resolution, microslip, and repeatability. So for the Sharpie test, it simulates high accelerations. Joints will be subjected to an industry. The prototype screws into the Sharpie base, and the tester delivers impact force to the top plate while fixing the bottom plate. And then the optical sensor measures microslip in the top plate that results from the impact. So next, we have the Intron tensile testing machine, and it's a static tensile loading machine. It tests shear strength of the joint. It does fatigue testing, and the sample used in the machine is symmetrical, so shear force is distributed evenly through the system. And then finally, for our plans for this upcoming semester, it includes initial actions and a design loop. So initially, we will set up testing protocol, order parts, build a Sharpie tester, build our prototype, and this leads us into our design loop, where we run tests, we analyze the data, and we point out weaknesses. And then we can either make tweaks to the prototype or order new parts and build another prototype. And that brings us back to running more tests and gathering more data. So this will be our focus for senior design 2.